Hi everyone, and welcome to a new video about control system topics, and we continue with the subject of stability, and in particular with the Routh-Hurwitz stability criterion. And in this example we will again do some calculations and verify our calculations using the simulations. But in this case we will look at a different problem, and this is the problem what we have. We have the following transfer function, which is shown here for the open loop GS, and this is placed in a multi-feedback configuration. So what we have is a GS, which is the open loop, which is in cascade with a K1, which is just a gain, and it is now fed back here with a value of K2, which is the minor loop in this case, which is also called the inner loop, and that is in cascade with the integrated, and again the total is unity fed back here at this summing point. So we have now two parameters, which is also the question in place here. Determine the values of K1 and K2, both of them, such that the closed-loop system is stable. Again, we have the situation of stability, but this time not one, but two unknowns. So we need to tackle this in a somewhat different form. So let's look at the situation first, step by step. Again, what we do is we determine the characteristic equation of our closed-loop system. Now, since this is a somewhat complicated diagram, let's first simplify the situation by making a selection of the diagram. So I will take this part of the system, I will just call it A of S, and I will make a transfer function of that one using Mason's gain rule. So I have the following: the inner loop or the minor loop is A is equal to K1 times G, which is just a forward path, divided by 1 plus the loop, and loop is K1 times G times K2, and I'm back again at the same point. So that's actually 1 plus K1 times K2 times G, as this is the loop transfer function. Now if I now substitute the values which is given here for the G, I have the following expression. Now if I simplify this further by multiplying the numerator and the denominator by s minus 2 times s plus 4, I have the following expression. And this is now the expression what I will use for A of S. Now, since this is now just A of S, this is completely just one block, I can now continue with the outer loop and the major loop actually, and this is just a simplified form, and that will be in cascade, so AS will be in cascade with this integrated part, which is 1 over S. So what I have now, the total transfer function, which is now called the TS, is again the same formula of Mason, which is AS in cascade with the integrated, so which is the forward path, which is shown here, AS times 1 over the S, so integrated, divided by 1 plus a loop gain, which is again AS times 1 over S times 1, which is just the unity gain feedback. So this is actually the expression. Now if I just simplify this, multiply the numerator and denominator with S, I have the following expression, and I can now substitute the value over the expression, of A of S, which is now shown here in the following expression. Of course, we need to simplify this in order to determine the characteristic equation. So I now multiply again the numerator and denominator by this part of the expression, which is S minus 2 times S plus 4, and then plus 8 times K1 times K2. Now this is now the much more simplified form, and this is now the denominator I need to determine our characteristic equation. I will now equate this to 0. So that is actually our next part. So the characteristic equation, I take this and equate that to 0. So this is the situation. Again, this needs to be simplified because I need a polynomial expression, not an expression which is factorized in this form. So I will now move on to the next step. And if you do several steps, you will get this. So what you see is it's a cubic third order polynomial. We have an s to the power 3 plus 2s squared plus 8 times, in parentheses, k1 times k2 minus 1. And there's s here, I forgot this. So there's an s here, and plus k plus 8 times k1. So just 0. Now, if I move on with this analysis, because I need the characteristic equation to determine the stability. So we generated a Routh table. So what we do is we use this, we generate the Routh table. For that, I of course look at the first column, but I need A3, A2, and also A1 and A0. I got this from my characteristic equation, but I also need B1 and C1. So let's again, to memorize what we have here, so let's put it here. This is the third order polynomial in general form. This is what we had. So again, here, the S is placed here. I forgot it in the previous slide. So these are the coefficients. So A3, A2, A1, and A0. So I can now place this in here. Before I do that, let's calculate B1, B2, B3, and then C1, C2, and C3. So let's look at this row first of S to the power 1, which is then the analysis shown here. So B1, again, the similar expression what we used in the previous examples. You just make a matrix of these four elements. You take the determinant of that, place a minus sign, and divide by the A2. Just substitute the values of coefficients. Now you do the math, you will get this. This is the expression which you have for B1. Now B2 is again a similar form, but you will use these two, and these two. So you shift actually one column to the right. And you will get a 0, and B3 is also 0. That's most of the time the case, that you get a B1 a value, but B2 and B3 will be always 0 in a third order system. Now, I can now continue with the expression for C1, so I and C2 and C3. So I will now use a row of S to the power 0, which is now verbally worked out here. So C1 will be this, again, a similar expression. I use these four elements in our matrix, and I determine the determinant and divide by the B1. It's actually on top of C1. So if I now just substitute the values, I get this, and if I now simplify this, I get 8 times K1. Now C2 in a similar form, again shift one column to the right side, but you will get a 0 here, and for C3 also 0. So I have now the necessary elements to set up my table and also check the first column in the next steps. So I have now this in here and this here, 8 times K1 in here. So let's do that. Let's generate a table in using this value. So I have now 1, 2, which is just here, 8 times in parentheses K1 times K2 minus 1, which is just A1, and then A0 is 8 times K1, which is just here. So I have now the B1, and I have also the C1. Let's check now the situation in first column, evaluate the stability. That means the following step, evaluate the stability stability of the value of K's for stability. So this is actually K1 and K2. So what I need to check the situation that there is no sign change. So if I don't want a sign change, it means there is a plus here, a plus, and there is a, it means it needs to stay positive, and it needs to also stay positive. So I have two conditions for this row, for this column. So the Routh table says actually we see that we require the following conditions to have no sign change, which is actually this one. So 8 times K1 times K2 minus 1 between parentheses minus 4K1 must be larger than 0, and 8 times K1 must be larger than 0. Both of them are required. So if I now just simplify this one and that one in expression, I get K2 must be larger than 8 plus 4K1 divided by 8K1, and this is just divided by the 8 left and right hand side of this equation. Then you will have the K1 must be larger than 0. So K1 is definitely larger than 0. That's one of the conditions we already have. But what we have now is the K2 is this, and I can simplify this. Of course, I get a 1 over K1 plus 1 over 2, so it's just a half. So I have K2 must be larger than 1 over the K1, which is the value what you get here, plus another half. Now, this is what we have now. Let's now move on to the next slide, and I will take this and also take the table what I have here, and I will continue with my analysis. Let's work on this in more detail. So again, we have this situation. If I now substitute some values for K1 and do some examples. For example, if I now have K1 is 0.1, which is larger than 0, so I satisfy this condition. Then K2, if I just substitute the values, I get 1 over 0.1, which is 10, then plus a half, it will be 10.5. Okay, so I need that the K2 must be larger than 10.5 if I have a value for K1, which is 0.1. Now, if I now increase the value, for example, 0.5, again, substitute the values, 2.5. So by increasing K1, you will decrease K2. So there's some relationship between them. Now, if I move on, I say K1 is now 1, so a little bit larger, then this K2 will be also a little bit smaller. So this will decrease as you increase K1. Now, let's check this, if this is correct. Now, K1 is now 10. That is 1 over 10, which is 0.1 plus 0.5 will be 0.6. Okay, if I make it 100, the next one, then I will get, for K1 is 100, I will have then the associated condition is K2 must be larger than 1 over 100 plus 1 over 2, which is 0.51. So what you see, actually, there is a pattern. So if I now collect this, of course, I can continue up to maybe 1 million, but you see already a pattern. I say the following pattern. If K approaches infinity, very large values, the K2 is actually left with this 1 over 2, so 0.5. So this will disappear, but I still need to make K2 larger than 0.5. So, for example, if you make it 1 million, and then you need still have your K2 larger than 0.5. That's actually for this condition. So we can also evaluate this using a graph. You can plot this because there are two conditions, and with this problem with the two conditions, you can make a sketch where you have actually a plane where you see the stability. So let's do that in the next step. So if I make a plot by placing the K1 on the x-axis and a K2 on the y-axis, so I say K1 will be here and K2 will be there. Now, if I look at the expression of K2, which has an inverse relationship with K1. So if I increase K1, this will decrease, and if I reduce K1, K2 will increase. It's also seen in this analysis using these examples. So what we can say is K2 will have a shape like this red curve. So it will also have an asymptotic line because it can never be smaller than 1 over 2, 0.5. So that means actually that there is an absolute minimum, and I cannot go under this 0.5. Now, if I want to satisfy the condition of this K1 is larger than 0, I need to stay actually on the right side of this vertical line. So everything on the right side of this vertical line is allowed. If I'm on the line, I have, of course, a situation where we have a marginal stable system. If I want to, of course, satisfy and this condition for K1 and also the condition for K2, I need to also check for this line, because this line is also a very important boundary, because I want to satisfy both conditions. So what I then should do is, if I'm at this line for my values of, for example, if I take this point and I say, okay, let's make a drawing of that. If I say, okay, I will take this point, for example, that has a corresponding K1, which is just something, and this is another value for K2. So this is actually a collection of K1 and K2 values. But that is also at the edge, and it will also produce a marginal stable system. And it will be, of course, produce a sustained oscillation at the output. If I want a stable system, I need to be above this line. So everything above this line, and also above this, all those area here, so I can also make a sketch of that one. So everything here given, that is actually the area of stability, or area stability. If I'm under this line, under this red line for here or somewhere else, whatever, doesn't matter, I get for sure an unstable system, because I can satisfy for the condition of K1, but I cannot satisfy, for example, the condition for K2, or the other way around. So I can say, okay, I'm here, for example here, that will satisfy for sure K1, but doesn't satisfy K2. So we will, of course, look at this in more detail when we do the simulation in the next step. So let's go to the next step and verify our calculations using the simulation. So we continue with our simulation of our designed values for the K for stability. So let's check the situation in simulation. We define first our Laplace parameter S, and then we type in our open loop system, which is G is equal to 8 over S minus 2 times S plus 4. So that's actually our open loop transfer function. Let's also check that in zeros pole and gain, and we have exactly the situation as we also had in our example. Okay, what we can do, of course, is first develop that transfer function what we have called A. But in order to do that, I need to have A is equal to feedback, and then I can say feedback, and I can say K1 times the open loop transfer function, that's the forward path, and then in the loop I have a K2, and then it is a negative feedback. But I don't know two things here. There's the K1 and the K2, so I have to also substitute that in here. So let's check a value for, select the value for K1 and K2. K1 is for sure larger than 0. That's actually the condition. So if I say K1 is just 1, just larger than 0, that's actually met, I can now play around with K2. I know that K2, the expression for that was K2 is 1 over K1 plus 0.5. That was the expression. And this is what we have discussed. This is actually the edge of the stable point. So you will get, if you have K1 is 1 and you make the K2 exactly 1.5, you will have the marginal stable system. If you want a stable system, then you need to make this larger than 1.5. So the K2 must be larger than 1.5. But if I move on with this one, then I have actually the situation for A. So I have now A is equal to feedback with K1 is 1, K2 is 1.5, and I have now this expression. Now, if I now want the total transfer function for T, which is now, again, feedback, it's the same configuration. Now I have in the forward path the A, which is multiplied by our integrator 1 over S. We have this seen this, and then in the loop I have only unity gain, so it's just 1, and I have again minus 1 for negative feedback. And this system, if you look at it, this is now the total closed loop system. You can see that there is a stable pole at minus 2, but this is these are pure imaginary poles. So we have a pole at plus J2 and minus J2. I can check that by saying pole and T. You can see what will produce that. You have a pole pair, pure pole pair, at plus J2 and a minus J2, which is of course called here in I, it's mathematically, but it is what we call in control system J. So we have now minus 2 as a stable pole, but this will produce a sustained oscillation at the output. So let's check that. Step T for this case. Step T. What do we have? Now let's make this larger. And I can now zoom in this part, for example. I have now the situation, and I have indeed sustained oscillation, as you can see. So this will produce a marginal stable system. Now if I now move on and say I can change now K2 in another value, so let me make it larger, so larger than 1.5, because it was actually at the edge. So let's make it 2, for example, and then run again the A. So I can say A is equal again this, so I can rerun this, and I can say, I can just copy this one, I can say again T, and now I get this one. What you see is, now I have no imaginary poles anymore, no pure imaginary poles. If I now do this pole, the new values, will be this. As you can see, we have indeed it's a complex pole, but we have a negative real part, so that will be of course under damped system. That will not produce a sustained oscillation. And this is just a pure real pole, which is stable. So if I now do step for this T, I see indeed it is not oscillating. It has of course some oscillations and also some overshoot, but it is not as oscillator anymore, so it is not oscillation. So this is confirming actually what we have seen in our analysis. If I make, for example, K another value, I will of course have to check again the K2, but this already proves what we have discussed earlier in our analysis. If I make, for example, K1 negative, I will also have an oscillation for sure. I mean an unstable system for sure, because then the K2 will never K2 will never make the system stable, because I also need to meet K1 must be larger than 1. If I now make, for example, K2, and that is the last form, make it unstable, so let's make this K2 smaller than 1.5. So for example, I make it 0.5. So I make this. Again, I'm going to evaluate A, so with the new values, and T also, so I get a T here. Now what you can see, we have now this following transfer function. It's not maybe visible at the moment. Let's first check the poles. So poles for this. You see there's a stable pole here at minus 3.7 approximately, but these two are for sure unstable because we have a positive real part. So if I now make that in the step also T, you can see that, and if I now make it larger, you can see that this is out of control. So this is 3 times 10 to the power 25. It's already blowing up after approximately 70 seconds. So this is actually not a stable system. So it will produce an unstable system. Now we have now seen that this is indeed correct. So you can also make this, of course, in a different form. You can also make a pole zero map. You can see where the poles are located. That's actually visually. So you can see one of the poles is here. Another pole is there. Again, this shows in a pictorial form, in a graphical form, and you have also here that in a numerical value. And this is our real pole. Okay guys, this was for this example with the calculations and also the simulation, where we have now verified that the K1 and the K2 values that we have calculated are verified in this simulation. So we have now seen a situation for stability with 2 unknowns, 2 gain values, K1 and K2. I hope this clarifies the situation also for this quite challenging example, and also with a multiple loop feedback configuration. If you have questions and comments, suggestions, please let me know. Thanks, and I see you next time in another video. Take care and have a nice day.